Welcome to our little introduction to the basics of fasteners and what's happening inside a bolted joint. So I'll step through the loading processes to give you an understanding of what's happening internally to each of the components in the joint. So let's start with the parts that we've got ready for assembly. We've got a blue part and an orange part, and they're going to go together with a bolted arrangement. I'll insert the fastener, put on the nut. I'll tighten that just to finger tight. And then when I torque it up, you'll notice that the parts themselves got a little bit shorter, a little bit compressed in the joint, as sort of indicated by the dimensions at the top, and the bolt got a little bit longer. And each of those got, they changed in length in proportion to their stiffness, as we'll see in a minute. So the parts are compressed in the joint, the bolt is stretched in the joint, that is in the material between the head and the nut, kind of effectively a slightly longer length is used, but in first order you can just take the length between the head and the nut. So if we consider the internal loading, well, you can think about the strain relationships in the parts and the fastener, and think about how they are, what the geometrical constraints are that help us to understand what the loads are in each. So here I have back to back, I have the two sort of Hooke's law relationships that are happening. One on the bolt side, where we're elongating the bolt, and one on the parts, probably parts plural, where we've got the parts in compression. Now, in proportion to their stiffness, say K bolt, if we apply the bolt load, we'll get a delta bolt, and because we're applying that load to the part, we've got a P part, and in proportion to its stiffness, we get a delta part. So that just means that delta part is the amount by which the parts in the stack compress, or deflecting compression, and delta bolt is the amount that the bolt elongated. And you'll notice that they're not the same, and they're in proportion to each of their respective stiffnesses. The fact that the bolt load in tension and the parts load in compression are the same, that's just the preload amount. So forces are balanced in the parts and the bolt. The parts compressed in proportion to their stiffness, and the bolt elongated in proportion to its stiffness. If we now introduce a tensile external load working to separate the parts, how does the internal loading respond? So here we are, we're set up, ready to apply the load. We have this relationship that we understand between the delta of the part and the delta of the bolt. And unless the parts are going to separate, the tendency to stretch the bolt is going to be equal to the tendency to relax the compressive deflection on the parts. So having applied the applied load, the bolt got a little longer again, the parts got a little longer as well, that is, the compression between them decreased, and so in proportion to their stiffnesses you'll see that the load changed. So the load in the bolt changed by a little bit, the load in the parts changed by a little bit, and proportionally, because the parts in this case are stiffer, the load in the parts decreased more. So that's expressed in this this relationship, this geometrical constraint relationship, that the change in delta part is the same as the change in delta volt. They both actually got longer. So the fastener load increases much less than P applied, provided the parts are stiffer. The stiffer the parts are in comparison to the bolt, the less the bolt load increases with applied load. In fact, if the parts were considered infinitely stiff in comparison to the bolt, when you apply a load, the bolt wouldn't see any increase in load until the parts become completely unloaded. But we'll go on to that next. So if we're going to increase that load significantly, what's going to happen? So here we've increased the applied load until the parts are on the point of separation. So there's no more load left in the parts, the stack of parts. Hooke's law for the parts no longer applies unless you consider the stiffness to be zero. The applied load in the bolt is equal to the applied load externally, because there's no other contribution to the load, so delta volt basically equals P applied divided by the stiffness of the bolt. So with the parts separating, where does the additional unit of force go? The additional force is going entirely into the bolt. So this delta bolt is increasing directly in proportion to the external applied load at this point, which is a point where the bolts are very vulnerable to fatigue loading. So a 10% increase in the applied load equals a 10% increase in the bolt. With a bolt being a thing that has threads on it, stress rises. It's not really a good situation to have all of that being carried in tension on the bolt. So it is the reason why we try not to ever get into that situation. We try to make the preload adequate, and the knowledge of the parts being bolted and the stiffness of the bolts is used to make sure that we've got a good bolt design. So what we're going to do next is we're going to apply some of that additional load so that it goes into the bolt. And you'll see that attempting to increase the bolt load to the point where the bolt capacity is exceeded will result in rupture. The bolt's ruptured, it's broken apart, P applied has disappeared, it's vaporized. We went through the red X there, and somebody might have got hurt. Anyway, that's the basics of bolt load mechanics.